Accelerated Algebra 2, Stirrup here. So we're going to be doing a 6b. So let's move that down. So we're talking about polynomial functions and their graphs. So there's a lot of vocabulary comes in this chapter. So let's make sure that we feel good about it. All right, a polynomial function. Polynomial functions are just a string of things with x's or y's going out. So we have the different degrees. The degree are the exponents. So the degree are the exponents. And then you have binomials, which you'd have 2 terms, trinomials at 3 terms. And there's other Latin root terms like we could classify it as, but we'll get into those a little bit later. The leading coefficient, so you look at whatever your highest exponent is, your leading coefficient would be out front. So this would be leading coefficient of 3. It would be a 3rd degree polynomial. It would actually be a trinomial because you'd have 3 terms to it. Leading coefficient here would be root 7. That would be a 4th degree polynomial. And it would be a binomial in this case because there's only 2 of them. The constant term is just when you have a number. That's whatever's at the very end usually if it's written down in order. Okay. So standard form of a polynomial is going from the highest exponent to the far left and counting it down to the lowest exponent as you go to the right, with the constant, if there is one, being at the far right, making sure you keep all the signs the same. Okay, degree 0 is like a constant, so that would be like, 5 or 7 or -2. Those are constants. Linear, we've dealt with that, so it's just mx plus b. Okay, something raised to the first power is linear. Quadratic is raised to the second power. Cubic is raised to the third power. Quartic is to the fourth. Quintec is to the fifth. It keeps going. They have Latin roots for it, but it's not the most important part of it, but I guess you should know constant through quartic just as far as having vocabulary goes. And again, you want them all in degree order. And I remember when I used to look at this when I was in your grade, going, what in the heck is all that? Well, a sub 2 or a sub 1 or a sub 3 or a sub 4, they're just numbers that would have been there. And I don't know why they never tell us that, but I guess I'll let you know now. So hopefully that'll clear things up. Okay, completing the following. Decide if the function is a polynomial. Decide, okay, so, and then we want to, let's see. So yes, this is a polynomial. Let's rewrite it in standard form. So I have -2x to the 4th. That was the highest. And then minus 3x squared. Then minus 9x. Minus 7. So we're just going to call this a polynomial because we have more than 3 terms. I'm sure there's a Latin root to it. But because it's raised to the 4th power, it's a 4th degree. Okay, and again with this one, this is not a polynomial. The reason it's not a polynomial is what would happen with that is that has to come down here. And as soon as a variable becomes a denominator, you no longer deal with a polynomial function. So there's no reason to go any further on this one. Let's move on. All right, all of these are polynomials. Let's write them in descending order. So I get -3rd root of x to the 4th. The x to the 4th is not underneath the radical, so that means it's a polynomial. Plus 1/8 x to the 3rd plus 2 over 3x. So this is a 4th degree. There's 3 terms, trinomial. Okay, and again, this one is going to be a polynomial. So I have that to the 3rd. That was my highest exponent. Then 7x squared plus 2x minus 7. So this is a 3rd degree polynomial. This one is not going to be a polynomial because I have the square root of x right there. So you can just stop right there. It will not be a polynomial. Though it would graph, it's just your graph wouldn't follow the same rules. All right, so use direct substitution for the following. So I want to plug in -3. Another way this could be written is they could write it as this. These 2 terms are the same thing. Okay, so what we're going to do is we're going to plug that negative 3 in. And let's see if we can do the math. 3 to the third power is 27. It's going to stay negative. That's going to give me 9. 9 times negative 2 is negative 18 plus 9. And I don't have a calculator with me because I'm sitting outside doing this. It's beautiful out, so that's going to give me 135. So negative 135 minus 18. Let's see, minus 9, because if I combine those together, I get minus 9. So that's going to give me negative 144. So that's the value of what it comes to. If I had wanted to graph this, if I had graphed this polynomial, the point negative 3 comma negative 144, which you'd never see on your graphs because usually most of them in class we go from negative 10 to positive 10 in the xy direction. But this point does exist on the graph. But this, for the most part, when we substitute it in, we get negative 144 for an answer. Okay, synthetic substitution. This is going to become your friend, okay? So what we're going to do is we're going to take this right here, and we're going to have it outside, and we're going to have this L-looking bracket. So what I'm going to do is I'm going to take all of my lead coefficients, and do we have any missing? I don't have an x to the third, so where x to the third is, I'm going to put 0 in. So I'm going to go at 2. I'm going to put a 0 because that's where my x to the third would be. A negative 8, a 5, and a negative 7. Okay? Now, do you feel comfortable where I got all this from? You feel comfortable that there's no x to the third term, so that would have to be a 0. Okay, this is how you do synthetic division or synthetic substitution. Very first step, you bring that straight down. Okay, you bring your lead straight down. And then you're going to go 2 times 3, and that's going to give me 6. And we're going to add this together now. 0 added to 6 is 6. And 6 times 3 is 18. We're going to add straight down. Negative 8 plus 18 is 10. 10 times 3 is 30. Add this straight down, so I get 35. 35 times 3 is 105. Negative 7 added to 105. What is that? 98. Okay? So what this is, this value here, the very end value, means that the point 3 comma 98 exists on your graph. Okay? Sometimes we want you to write back in so your x value, so we use division, we will reduce our highest exponent by 1. So if I reduce x to the fourth by 1, I get to x to the third. So I'd get x to the third plus x to the second plus x plus 35 plus x over 3. So this is kind of a little different thing to look at, but we can go over that in class and definitely talk about it. But synthetic substitution or synthetic division is a very good way. It does show you some points. It does give you some idea of what is going on at the graph at those different x positions. So steps in synthetic substitution, polynomial must be in standard form. So from highest to lowest as you go left to right as far as the degree, write the coefficient, including the zeros for any missing powers. That's like we did. We didn't have x to the third on the last one, so we put a 0 in there. And write the values of x on the left. Okay? And that's what we're dividing by. Okay, so we're going to do the same thing with this. We're going to divide by that. So I'm going to have a negative 3 outside. I have negative 1. I have a 1 at the x to the third. I don't have an x to the second, so I'm going to put a 0 in. I have a negative 1 because of this, and then a 1. So let's go through and do our math. Negative 1 comes straight down. Negative 1 times negative 3 is positive 3. Add straight down. That's going to give me 4. 4 times negative 3 is negative 12. Add straight down, so I get negative 12 down here. Negative 12 times negative 3 is 36. I'm going to add straight down. That's 35. 35. Come on, baby. 35 times negative 3 is negative 105. We're going to 105. We're going to add straight down, so I get negative 104. So the point negative 3 comma negative 104 exists on our graph. I don't know why it's showing up as 2. Okay, if we wanted to add back in our things, We started at the fourth power. Now we're going to have it to the third. So negative x to the third plus 4x squared minus 12x plus 35 minus 104 over the opposite of that, x plus 3. Oh, my handwriting is getting sloppy as I sit outside. I'm sorry. Again, if you have questions about this, talk to me in class. We can definitely cover these questions. Okay, so the end behavior. The end behavior. So let's just make a weird graph, something like this. Okay, so the end behavior is we're looking, where is this going? So as my graph goes to the right, my end behavior goes up. And if I look over here, as my x value goes to the left, my end behavior goes down. Okay, and so we talk to this way. So let's talk about this region over here. So as x approaches infinity, the function at x, that's your y value, goes also to infinity. And then I also have this one here, if we talk about this side, as x goes to negative infinity, because that's where we're going. This is going to negative infinity this way. The function at x is also going to go to negative infinity, meaning it's going to go down. Okay, this is great behavior. What you'll see on some tests district-wide is as you go to the right, the graph goes up. As you go to the left, the graph goes down. So it's pretty basic. So we're kind of giving you the mathematical perspective. Okay. Not sure what we're looking at on this graph. It's right there. Hello, Viv. So I'm not sure what this graph is showing us either. Oh, I think I know what we're doing here. Okay. So on this orange line, as x goes to infinity, f at x, the y value, goes to infinity. If I look at this side for here, as x goes to negative infinity, as I go to the left, f at x will also go to negative infinity, so it goes down. For this black one, as x goes to infinity to the right, function at x, the y value, goes to negative infinity. And then the end behavior up here, as x goes to negative infinity, then f at x goes to positive infinity, so it goes up. Both of these work in similar fashion. There's supposed to be an arrow here, but I don't know what happened to it. Okay, so what's going on here? As x goes to infinity, as I go to the right, f at x goes down to negative infinity. If I talk about this one here, as x goes to negative infinity, f at x also goes to negative infinity. Then on the blue one, again, there should be an arrow up there. As x goes to infinity, function at x, the y value, goes to infinity. And same here, as I go to the left, x goes to negative infinity, f at x goes to infinity. So that's talking about the end behavior. Where's my graph going to wind up as we go to the right or to the left? Does it go, and go upward, or does it go downward? Okay. So complete the statements for the end behavior. So what I would do on this is, this is a line. So you have -7, it goes up, right. So this is basically what's taking place. So as I go to the right, I go to infinity. As I go to the left, we go to negative infinity. That's the same thing with this one. If we were to graph this, we'd have +7 up here, down. So this is what the graph kind of looks like on that, just as a rough sketch. So as x goes to infinity, the y value, f at x, goes to negative infinity. As I go to negative infinity, as I go to the left, my graph goes to positive infinity. What about these? Well, this is a parabola. It opens upward. So as I go to the right, it goes to infinity. As I go to the left, it goes to infinity. As x approaches infinity, as I go right, the function at x goes up to positive infinity. As x goes to negative infinity, it goes down. And then this one is also a parabola that opens up. I don't care where the vertex and stuff are. I just know that it opens up because I have positive a values. So again, we're going to get the same answer on these. Infinity on both of those. And then you look at this one. So this is actually a graph that should be like x to the third. We haven't talked about that yet, but where is this going? As I go this way, it goes up. So as x goes to infinity, the function at x, or the function of x, some people say, goes to infinity. And then what about this? So as x goes to the left to negative infinity, the function at x goes down to negative infinity. Okay, try these powers without using a calculator. Let's use a graphing calculator to try these. Well, I don't have a calculator with me, so x to the third kind of looks like this. Okay, so that means that as x goes to infinity, f at x goes to infinity. As x goes to negative infinity, f at x goes to negative infinity. But this one, if I have a negative out front, this changes the graph. It looks like this now. So as x goes to infinity, positive infinity, the graph goes down, so f at x goes to negative infinity. As I go to the left, to negative infinity, my graph goes up, so f at x goes to infinity. Something that's raised to the fourth power, that's basically what it's going to do. If it goes negative fourth, it does this. So this looks like an x squared graph. So again, x goes to infinity, f at x goes to infinity, and it's the same thing with the other one. This one would be, I'll do this one down below for here. As x goes to infinity, f at x goes to negative infinity, and as x goes to negative infinity, f at x goes to negative infinity as well. Okay, x to the fifth is going to look like this, so it's the same answers as x to the third, or it's going to look like this with the negative out front. X to the sixth is going to do this, so it's going to be the same exact concept for both of those. So how do you decide on the end behavior on the right? So positive infinity goes up, negative infinity goes down. That's really all it is. How do you decide if the end behavior, when we go to negative infinity, if it's positive, it goes up, or it goes down for negative infinity? So you're looking at the ends of the graph. The ends of the graph. We're not worried about the stuff all in the middle. We're worried about the end behavior. Okay? So if polynomials in factored form, you need to add up the exponents, add the exponents to figure out the degree. So this is to the first right here. So I get 1, 2, 3, 4, 5, 6. So that's degree 6. Okay, and that's going to be 3, 4, 5, 6, 7. Degree 7. Okay, so you add up the exponents if it was in factored form. All right, so this is 6b. I'd say the odd problems are perfect. Have a great day, my friends. Take care of one another. Bye-bye.